Welcome everyone, and let's thank Mark for being here and presenting this nice seminar to us. He's coming from Simon Center, and he will talk about the random matrix theory and the black hole theory.
Yeah. Thanks a lot for the invitation and for all of you for coming. I'm doing a Blackboard talk so that it's more informal, and so please ask me any questions if there's something unclear or you have follow-up questions. Here's the title. It's based on a paper from July with Luca Iliescu and Gabor Sharoshi. So as an introduction, I'll talk about the context in which this we conceived of this work, which is the connection between black holes and quantum chaos. And these developments are happening at in the context of an even larger effort, which is the new frontier of quantum dynamics at high entanglement. And this is interesting because in current days, experimenters have exquisite control over quantum dynamics of many strongly interacting particles in certain setups, such as quantum simulators with ultra-cold atoms. In quantum computation, entanglement is a resource. And so if you want to do powerful quantum computation, you want to study setups where you have large amount of entanglement. And from the theoretical standpoint, we have new tools and frameworks, new solvable models where we can address some of these questions. So one picture to keep in mind is that the Hilbert space of a many-body system is huge, and we conventionally only access a small corner of this Hilbert space of sparsely entangled low complexity states. And this is where all the successes of the 20th century physics have taken place. Universality in phase transition. Yes.
So when you say we access in small part, well, typically it's not even properly called part, because typically in the multi-body system we measure just few of the particles, then the whole Hilbert space is a tensor product of these. So typically you don't access Hilbert space in something at all, but access density matrix or something like that, which is not a small part of the larger.
Yes, but what I meant here is that usually, for example, especially in particle physics, we're studying small fluctuations around the vacuum. And only in recent years have we been starting to explore finite energy density physics.
But you mentioned that we still have access to all of the particles.
And you are completely correct that usually we have even more restricted access. The effective field theory, or I mean, the successes of these spectacular successes of all these frameworks is confined to this corner. This is by no means trying to discount.
Another question, Mark.
Yes.
So what about it classically? Is it not true that the black hole will be also chaotic classically without any quantum physics?
Yes, but here we are going to be interested in the connection with quantum chaos. So within the framework of ADS here, where the dual system is a quantum system, even though at large n has a semi-classical description, we are interested in the fine details of quantum evolution. But it's true that there exists classical chaos, there exists classical thermalization, and all these things are interesting, but I'm just restricting to it. Okay, so how do we get out of this corner? One way to do that is to start and start from this corner and follow time evolution. Typically, time evolution, if you're not starting from an energy eigenstate, leads out of this low entanglement, low complexity corner of the Hilbert space out into the wild. Okay, and this interplay can be studied within the framework of ADS-CFT, which provides a dual viewpoint on these issues, where we can draw again the Hilbert space. Of course, these two Hilbert spaces are isomorphic, but we can think of this Hilbert space being geometrized in some sense through asymptotically anti-de Sitter spacetimes, and string theory in this asymptotically anti-de Sitter spacetime. But we best understand holography in these small corners, and here the small corner is small fluctuations around empty ADS. This is where most of our tests have been conducted. But in the current era, we're interested in the duality for generic states. And as Kobe mentioned, these would be dual to black holes. So we're interested in the quantum physics of black holes. Okay. And so one setup that you should imagine is sketched on the Penrose diagram here. This is an ADS Penrose diagram. The orange line is the asymptotic boundary. This is the origin of polar coordinates. We're imagining that the field theory is living on a sphere. And this is an initial value slice here. And I prepared some method distribution on this initial value slice close to the boundary. That encodes some particular sparsely entangled initial state. And typically, generic initial conditions lead to a collapse to a black hole. This method distribution will fall in and form a black hole. This is the horizon. And so we end up, okay, in this black hole. And so they, erase this. So this process of black hole formation from generic initial conditions has been understood to correspond to thermalization in the dual quantum system. So this is one instance of the connection between black hole geometry and quantum chaos. Only chaotic systems thermalize. And that's one of the hallmarks of their dynamics.
So when you say
Yes.
the initial state here is sparsely entangled, because it's a CFT, right? Even the vacuum state is highly entangled.
But by sparsely entangled, I mean, yes, from UV degrees of freedom, you have large amounts of entanglement. But what we mean here is, for example, subtracting the amount of entanglement that there is in the vacuum. So if you just have small excitations, then the finite part of the entanglement entropy scales only with the area of the boundary of an entangling surface, whereas in typical states it would scale as the volume. But you are right that strictly speaking, in quantum field theory, in any state we have infinite amount. But that entanglement is not very accessible for low energy probes. So yeah. I mean, this picture that I erased is mostly thinking in the many body context where everything is fine. But you have to take it. Okay, so that's one basic connection. And then it's a fruitful endeavor in ADS-CFT to ask, identify certain ubiquitous geometric features in the gravity side and ask what they correspond to on the field theory side. So once we establish this, we can ask more detailed questions. For example, the dynamics of long wavelength horizons fluctuation were understood about a decade ago to correspond to hydrodynamic transport of conserved quantities. That's called the fluid gravity correspondence. and it has taught us about both sides. Yes, and there are many such connections. Maybe since we already mentioned entanglement, let me have that on the board. So we can probe geometry with extremal surfaces, and if they are codimension 2 and anchored on the boundary, they compute the entanglement entropy of certain geometric subregions. So let me have a picture for that. So this is the boundary field theory space-time. This is time. And here's an interval whose entanglement entropy we're interested in. So this is the subregion that the experimenters are imagined to have access to. We go to the boundary of this subregion. In this case, this is just 2 points. We anchor an extremal surface, in this case, just a geodesic, which does something like this. So just to be clear, this was time, this was space, and this was the Bose extra dimension. And so the extremal area of this surface computes for us entanglement. And entanglement entropy is defined in any quantum system. It's a universal probe of the thermalizing dynamics. Okay, is there any questions?
So extremal varying in space-time.
Yes.
Right. In Minkowski space.
In Minkowski space-time. That's where so varying in the time direction gives us the maximality, and the varying in space gives us minimality. It's a saddle point. That's why I call it extremal, not minimal.
In your first 2 points, when you discuss black holes, does it matter for you whether it's large black holes or small black holes?
I will be studying large black holes. So one particularly important property of this black hole, it's a universal geometric observation, is that the interior of the black hole grows with time. What do I mean by that? One way to assess this question is to anchor a maximal volume slice on different boundary points here, 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 and then let me draw how they look. Something like this. Okay. If we compute the volume of these slices, it will grow with time, and it will grow linearly with time at large times. And the dominant part of this growth is coming from this behind the horizon, but somewhat near the horizon sliver of space-time. Okay. And so this brings us to the main question of the talk. So there's a geometric feature. Is a growing interior captured by maximal volume slices, and we want to know what does it correspond in the field theory. How can we capture this? Can we find an observable that is sensitive to this growth? Okay. So besides answering this question in QFT, we hope that this could help us with some aspects of the black hole information paradox, or even more speculatively, sometimes people connect this expanding space-time behind the horizon to expanding space in cosmology. That's a very speculative connection. I don't have much to say about it. Okay, so I guess I can now give an outline for the rest of the talk. So we will discuss 2 candidates. For this field theory of quantity, and then we'll be studying this question in a toy model called JT gravity, because it's a hard enough question. We need to simplify the problem, and Yes, okay, there will be many sub-steps of that, but let me not detail it, and then I will end with a summary. Okay, so 2 candidates. Candidate 1 is just entanglement entropy that we talked about. So we're imagining that the field theory is on a sphere of linear of radius L, and we take the subregion to be order 1 fraction of this sphere. So its linear side will also scale with L, and we get the following picture. So here we have entanglement entropy as a function of time, and also I will also plot the volume as a function of time.
But the surfaces you're drawing, they're codimension 1. So.
Those are codimension 1. Question is, does entanglement entropy codimension 2 guys track this linear growth or not? Okay, so of course you need some quantity to give that make the dimensions correct. You use the ADS. Okay, so this is what the volume does. After some transient behavior, it grows linearly forever from the gravity computation. What does entanglement entropy do? It does something rather similar until some time when it saturates. And the saturation time is of order L. We have no reason to expect that some gravity effects would kick in at this scale to change the behavior of this blue line. So entanglement entropy fails at capturing this growth for all times. At early times, it does a good job. At late times, it does not. Even though it's a somewhat detailed observable that is extremely hard to measure, it's not sensitive enough to capture this long growth.
But it does a good job in the sense that it's just 2 straight lines, or there is some coefficient which matches.
No, there's no coefficient that matches. Yeah, it's not a very spectacular one. But at least the initial thinking was like this. I spent a couple of years of my career understanding actually the details of this wide curve, but for us, at this very crude level of discussion, it's just both are linear. The important thing is that entanglement. So, okay, maybe it's now the time to discuss some time scales. Okay, so if we try to, if we study just 1-point functions, they would reach in this setup. They would reach their thermal equilibrium value. They would stop evolving at the time scale of order beta, the inverse temperature. You're studying a pure state, but it has an effective temperature. And so they would stop evolving here, or if you have some inhomogeneities from here on, hydrodynamics would apply. So 1-point functions are the most crude observable. If you're studying something non-local, such as entanglement entropy or correlation functions at wide separations, they will saturate at timescales of order L. And in recent years, it turned out that it's advantageous to go to longer times, find more subtle observables that are sensitive to longer times. One such time scale is of order log S, where S is the entropy of the final corresponding entropy of the final black hole. In ADS CFT, we have large N systems. This is of order log N, whereas these guys are order 1, order N to the 0 in N counting. Okay.
That's not ADS though.
That's not ADS. That's field theory sphere. Okay, and yeah, I didn't manage the blackboard well. Sorry. We can, of course, this is not a linear scale. This is, yeah. And so here I will write the time scale S. So that's, for example, that's the page time of an evaporating black hole. And then from the old days of quantum mechanics, it was already clear that the time scale e to the S is somewhat important. This is named after Heisenberg, so it's pretty clear that it's something odd. So what happens at e to the s? Oh, I did. Yeah. So I didn't say how to access these timescales. So this log s timescale is called the scrambling time, and it can, and the ordinary correlation functions are not sensitive to this, but so-called out-of-time ordered correlators are sensitive to this timescale. So that's something extremely hard to measure, but it's some subtle observable, and if you study it, you can see the system evolving at a much later times. We talked about this. This is in the page time. You have to study some evaporating setup to access it. That's one way. Other way is so-called spectral form factor that some people may have heard about. What happens at the Heisenberg time?
Same as Poincare recurrence?
No. So Poincare recurrence time is even e to the s. And okay, so first let's talk about the Heisenberg time. So Heisenberg time, the best way to think about it is that at this time, the state, even though it was some out of equilibrium initial state, for all intents and purposes, has become a random state, only constrained by energy conservation. The reason being that any phase that you may encounter, something like this, phase difference between energy eigenstates, so these are energy eigenvalues, En and Em. This has become order 1 by this time scale. The reason being that the typical separation between energy eigenvalues is e to the minus s. Time is conjugate to energy separation. So if you multiply e to the minus s with e to the s, then you get an order 1 number, e to the I order 1 number. It gives me a random phase. So because the non-trivial information is encoded in these phases, we have lost all this information by this time. And so any sensible observable that you can conceive of should stop evolving at this time. And then, of course, there's the Poincare recurrence time that Sergei mentioned. And by this time, somehow, this was an approximation, and you regain phase coherence, but you have to wait extremely long. And I don't know of any sensible observable that captures physics at this time scale.
Where does the Lyapunov scale enter?
Lyapunov scale is this. So, and yeah, so the scrambling is this famous Lyapunov growth, and that's happened at this time. And we will be trying to understand. We will try to understand the physics of the interior at these times. Okay, so the failure of entanglement. Yes.
Why are the energy eigenvalues unknowable to order e to the minus s? It's fine if the phases evolve to order 1, right? As long as you know what they are. But you must claim that.
But so you imagine, so in chaotic systems, it's imagined that the energy eigenvalues follow some random matrix statistics, but the typical level of spacing is order e to the minus s. So if you have, any non-equilibrium initial state is some superposition of energy eigenstates with some phases. If all these phases by this time has become completely random, then you forgot about the special information that was there in the initial state. That's it.
Yeah.
And this actually leads to, like, if you make these assumptions, then you can actually derive thermalization at these time scales for correlation functions from just this assumption. This is called the eigenstate thermalization hypothesis. Well, you have to assume something about matrix elements as well, but roughly this is the ballpark. Okay, so the failure of entanglement entropy to capture this growth was the motivation for Susskind and collaborators to introduce something very unfamiliar to quantum field theories. which is called complexity. We won't need the precise notion, but I will just explain a little bit about what this is about. So we imagine that we have a setup where we have a finite dimensional Hilbert space, so something like a spin train, and we are handed this state psi of t by somebody, and we also have a quantum computer, which is initialized in the product state of spin-ups. So we have L lattice sites and we have spin-ups. And so we have a quantum computer. We are handed this, and our goal is to construct or write a program that implements the following computation. Starting from here, obtains this with the minimal number of gates. So complexity is defined to be the minimal number of so minimize over the gate or number of gates that constructs for you from this product state the state psi of t. And so the time dependence comes from this label on the state t. And so this is extremely hard to compute because you're just given two vectors in the Hilbert space. Your quantum computer can only do simple 2-qubit operations. You somehow have to find a way to get from here to here. And you have to minimize the number of gates to use in this process. Okay, but there is some expectation of how this quantity behaves. At early times, the idea is that the best way to simulate the time evolution is, or create this state from this state, is to construct an approximation to the actual time evolution. So the quantum computer can do this the following way. We construct an approximation to the Hamiltonian, multiply it by some small delta t, and then repeat this computation t over delta t times. So this is an approximation to the time to the exponential, and so we need t over delta t layers of these gates, and so we need for the linearly growing number of gates to obtain from this initial state this time evolved state.
But it's for any state psi, you're imagining this?
Yes.
You want to get from all spin up to any sort of general state in the same Hilbert space.
Well, so psi of t was obtained by time evolution, and but we don't have the same Hamiltonian with us. We just have a universal quantum computer. So we're not able to get the full Hamiltonian, but we're getting an approximation to the Hamiltonian. But this is not, so this is for early times. I'm not qualifying yet how early. And at late times, when the state has become random, it's conceivable that continuing this is not the optimal thing to do. So at later times, there are some shortcuts. Okay, and this later time actually turns out from general arguments. I mean, nobody can derive this in full generality, although recently there have been some very interesting toy models where people can prove lower bounds of complexity. But the picture you get is that you get linear growth. That's the linear growth here, and growing until the Heisenberg. Until the Heisenberg time. That's the expectation from complexity.
But now complexity is not a property of the system, it's a property of the state. So you assume here that all the state of the system will evolve in roughly the same way.
From if we start from low entanglement, sparsely entangled states, yeah. That's just the intuition that then in a chaotic system should forget about its initial state after some time. Yes, so I'm not treating my blackboard space very well, but hopefully you get this picture. So this second candidate has the rough features of the volume. It grows for an extremely long time linearly, and then saturates at the Heisenberg time. Whereas the classical result for the black hole interior volume that keeps growing forever. Okay, so these results about complexity lead us to the question whether there is some new quantum gravity effects kicking in at the Heisenberg.
But again, is there some kind of quantitative agreement there in terms of coefficient? There's something to compare?
Well, because complexity is so murkily defined, I mean, people made attempts, but I wouldn't say that there's that much. It's just this linear growth and saturation. And I won't need any of this, and I won't need to define this in quantum field theory. We will be mostly studying the black hole problem and ask, okay, what it actually is, what is this complexity for our toy model? Okay.
Fair enough. Right.
Yes.
Just be sure. So the definition of complexity would depend on the choice of this H2C.
Yes.
Okay.
Yeah. It depends on the gate set that your quantum computer has. And so depending on this and your error tolerance, all these go into it. And it's a bit murky.
I see. But then the point is that the linear growth is independent of this choice.
Yeah. But the coefficient would be dependent, or there would be some offsets. It's just some rough intuition. But what this rough intuition gives us, why I'm discussing it, is that even this complexity, some extremely esoteric object, stops growing at e to the x. And so it's natural to ask, okay, does the volume also stop growing, or that grows forever? That's the question. And so is there some new effect in gravity that stops the growth of volume? And we will find that there is.
But is it also the time where on gravity side, one should stop worrying about non-perturbative effects?
Yes.
Right? So
Yeah. So in gravity, this is going to be the like suppression of instantons, and so at this time it would turn out that instantons become important. Yeah, that's the punchline, and that in this toy model in JP gravity we can actually compute the effects of these instantons, and we'll find that the blue curve flattens out and saturates at an exponentially large value.
Sorry, Mark, could you repeat again? So the volume is exactly, what is it exactly?
So so volume is you anchor something at time t, and then you compute the maximum volume size. And this is okay in classical gravity. We will go to quantum gravity, define something that is well defined, like a gauge invariant observable in gravity, which in the classical limit reduces to the volume, and we will compute its expectation value in full quantum gravity in a toy model, and that will show the following behavior. It will grow just like the classical answer for a long time, and at the Heisenberg time, the instantons will make it flatten out and behave just like expected from complexity. That's the preview. Yes.
I mean, well, I mentioned that growth and volume has some physical meaning, but the meaning of complexity, physically speaking, what it is. Because I would say that in normal ASCFT, what I would get is the surface, not the volume, because all the information should be encoded in a theory of one dimension less. So why do we now pay attention to a volume?
Well, the volume is the gravitational language, or the So there's a field theory quantity unknown currently to us that translates in the gravitational description to the volume. I'm not saying that, there's a different quantity that this volume is equal to in the field theory description. And I will write that quantity down. And it's questionable what its actual relation to complexity is.
Your real Tagliani formula, something like that.
So the real Tagliani formula says that the entanglement entropy of a density matrix is equal to an extreme. So something like that. There will be some field theory object related actually to spectral information about the field theory that will be equal to the volume. Yes. Okay. Yes. So let's go to our toy model. Let me show you what we do. So we need to simplify this problem. This is completely intractable in 10-dimensional supergravity or string. We don't know how to define the volume. We don't know how to compute. So one way to simplify the problem is to go from this picture, which has matter and gravity, to pure gravity. And in pure gravity, you can arrange for a similar setup without infalling matter fields, following Hartmann and Maldacena, by taking an eternal black hole. This is half of the Fermat's diagram of an eternal black hole. We know exactly that in ADS CRT, the field theory dual of this is a thermofield double of 2 copies of the CFT left, right? And you can see a very similar geometric picture. The maximal volume slices going from the left to right CFT look like the doubles of those of the upper board. Okay, so you anchor these maximal volume slides both on the left and the right, and then you just draw it. And so this is simpler. We understand exactly the unique boundary theory pure state that this setup corresponds to, and we can have this without having matter. Okay, so that's one simplification. And the second simplification is that we want to go to as low dimension as possible because we know that lower dimensional gravity is simpler.
Sorry, Mark.
Yes.
So in the presence of matter, do you imagine something that you would compute is something like the quantum extremal surface, but generalized to this?
Well, I mean, there's a question of how the only thing that you have to have is that in the presence of matter, in the classical limit, it should reduce to maximum volume size, and then you can go ahead and try to define something.
But would you expect something related to something similar to this quantum extremal surface?
Well, quantum extremal surface, there's a natural notion of field theory entanglement entropy in the ball. Here, I don't know what field theory quantity you associate to a full time slice. So I think I would still go with just the definition of extremal surface. I wouldn't include any method. But I haven't thought much about it. Okay. So we want to go to low dimension, and the lowest we can go, where we still have black holes, is 2 dimension, and so we will have this we have studied 2-dimensional Jacob-Teitelbaum gravity. So there's 2 ways to think about it. One is that we just go to a toy model and don't care about where it's coming from. But Jacob-Teitelbaum gravity is also the effective field theory of the near horizon region of near extremal black holes. So near extremal black holes have ADS2 cross some compact space geometry, and if you do an S-wave reduction here and only keep the lowest energy modes, then you get this action. Of course, we will be studying instantons in this effective field theory, and from the perspective of the higher dimensional theory, this is an uncontrolled approximation because there are many other corrections in effective field theory. But that's what we're going to do. So the leading piece of the action is just a topological term, the black hole entropy times the other characteristic of this 2-dimensional manifold. And then there is the interesting dynamical part of the action, which is this is a dilaton gravity theory. There's a dilaton multiplying the Einstein-Hilbert term plus cosmological constant. And there's also some boundary term that I won't write now. Okay, I'm running short on time, so I will try to go quickly through the essential features of the model. The big simplification in this model is that the dilaton appears as a Lagrange multiplier. So if we integrate it out, so we're imagining that we're doing the Euclidean path integral for this, both integrating over all metrics and all dilatons. This is the Lagrange multiplier. If we integrate over it, then we just impose r plus 2 equals 0 as a function or delta function in every point of the manifold. So we are studying, so this integrating this out fixes r to be minus 2. So we are studying hyperbolic Riemann surface. Okay.
You have to integrate phi over the imaginary axis.
Yes. Yeah. So I mean, people don't understand. Like, let's just define the theory as having this integration contour, and nobody has studied in detail whether this rotation of contour is justified. But it gives us a really nice final result, so we kind of like it and go with it. So the famous paper by Schenker and Stanford computed this path integral to all orders in the genus expansion. Let me just sketch. Well, actually, I drew something here. So SSS obtain the following. Okay, so after integrating out the dilaton, we are left with the following. So we want to calculate the partition function, where we imagine that the asymptotic boundary is of renormalized length beta. So this is the usual thing that you compute in ADS-CFT. So how does it look? Let's just go to genus 0. This is a cartoon of the Poincare disk. So we are studying genus 0 Riemann surface, hyperbolic Riemann surface. That's the hyperbolic disk. That's the Poincare disk. We have a boundary whose length is beta. So that would be a cutout from this hyperbolic disk. Okay, and so we have to calculate the action of this. So we get this contribution, and then we have to go to higher genus. Okay? We have to sum over all genus. From that genus counting parameter, we get an exponential suppression in S0. Okay, hyperbolic Riemann surfaces have some moduli, and we have to integrate over all moduli. That's a finite dimensional integral. So far, so good. And we also have these degrees of freedom, which correspond to how we cut out the asymptotic boundary. I will call them wiggles, and they come with some action. Okay. And at higher genus, what we do is, okay, we have a hyperbolic Riemann surface with this kind of wiggly boundary. We cut it up into two pieces along the geodesic, this blue geodesic, that's length d. Once we cut it out, we have this shape, which is referred to as a trumpet in the literature, which is characterized by two numbers, beta and b. Of course, you have to do the wiggle path integral for these fluctuations. These are boundary gravitons for those of you who know low-dimensional ADS-CFT. But on this side of the cut, all we have is the integral over all moduli and the bordered Riemann surface with one boundary of length p. And so this is an object studied by mathematicians, and we'll just call it the moduli space, the volume of genus G, Riemann surfaces with one boundary of length p. And okay, this is a well-known object in math. So what you get from here is, and then we have to glue these things back together. We have to integrate over P. So what we get, the measure actually turns out to be PPP. We get this trumpet contribution characterized by two numbers, beta and B, and then this volume of the moduli space G1 comma B. Okay. Any question about this? Okay, and then you can write down very simple Gaussian expressions for these guys. It's really simple. Now the only catch is that these modular space volumes are hard to compute, but modern developments in mathematics have discovered an interesting connection between these modular space volumes and random matrix theory. And the results of Stanford is that this whole genus expansion can be resummed in terms in the matrix model language. And what one gets is the following. So we get a matrix ensemble. There's some potential. So we integrate over all Hermitian matrices with some measure. And this Z of beta is an observable in this matrix ensemble. And if you think about H as a Hamiltonian, then it's very natural that it would be the expectation value of space e to the minus beta H. Right? Because this is the term of, this is what Z of beta is in one quantum system. If you have an ensemble of Hamiltonians, then and you know the measure, then this would be the expectation value. I mean, the partition function must be the expectation value of space e to the minus beta H. Okay, so this is not my result. This is SSS result. And what we did,
where you weight every contribution from every theory, how does it look the VH? The way of weighting every little partition function.
Yeah, you actually have to consider a double-scale matrix model. This potential is not really well defined. Only some renormalized potential for one energy eigenvalue is well defined, and it's some complicated thing. In matrix models, you don't really need this. If you have a large n, then the system is kind of solved through recursion relations, and the only thing you need to know is the density of states. And so that's what people usually talk about. And the density of states, which is, so this thing can be rewritten as d rho v. That's the usual physics definition of density of state. Okay. And this thing, if I tell you the genus 0 density of states, then from there, using the recursion relations, you can compute everything. And this density of states in this model is e to the s naught. There's some factors, I don't care. Sinh square root of e. That's the answer. So if I give you this data, if you wish, you can reconstruct this matrix potential, and you can compute everything. There are e to the minus s naught corrections to this. But you need to know a bit of random matrix theory. Okay. Yeah, I'm going a lot slower than I thought. But let me then just try to.
Why did you use the expectation value of the rho? Why do you say that the rho?
Yes. Yeah. And so rho of E for one member of the ensemble would be just the sum of delta functions. But if for every member of the ensemble, I get a different sum of delta functions. If I take the expectation value, so basically I'm taking the Laplace transform of this thing. Rho of E is an operator in this matrix model, and so that's why I use an expectation value to be able to write a function. Sorry, it was a bit garbled, I hope. Is that it? Yeah. Okay, so actually, the question that that comes naturally. So if there is a matrix model description of the partition function, the question we asked ourselves, is there a matrix model description of the volume? Okay, so is there something? So the original question mark that we had now translates into this. What is the, is there an observable? And if there is, what it is there an observable that in the matrix description that would compute for us the volume? Okay, I don't think I have time to describe how we get there. So we use very similar technology to compute L. So the Euclidean gravity path integral, we draw geodesics, cut up higher genus surfaces into lower genus. And at the end of the day, it turns out that so by manipulations in gravity, we obtain that this thing is related to, actually Massimo's question is extremely relevant here, is related to the spectral two-point function in this matrix sound function. So here I wrote down what the one-point function of the density of states is. And here, this L turns out to be related to the spectral two-point function. This is, of course, a number in any one instance of the ensemble. But then if you average over all members of the ensemble, then you get a two-point function, which is not the factor. Okay, so yes. So the density of states depends on an energy argument. E here is the center of mass energy, and omega is the energy difference. And so this guy doesn't have an omega in the E argument. So the way we will get an integral transform. Okay, so we will integrate over dE from 0 to infinity, omega from minus infinity to plus infinity. Of course, in practice, omega, the integral over omega will be focused on a small window around D, where we have an important denominator omega squared and a Boltzmann wave, which doesn't do much. And the time dependence comes from the following factor. So just like in the discussion of phases, time is conjugate to energy differences. So that's kind of making contact with that discussion. And so if we do this double integral transform of this density correlation function, then I'm telling you that to all orders in the genus expansion from gravity, these two expressions agree. Okay.
What is that? Left? What is this L of T?
Well, okay, I can. Oh, this is the volume. So
this is the volume.
This is the volume from gravity. So I just draw geodesics through these Euclidean metrics.
Classical.
So here, I'm doing quantum gravity, but the integrating over the Delaton fixed everything to be hyperbolic, and the only gravity fluctuations are these boundary gravitons. So those are taken into account, and then we have to sum over all G. And at the end of the day, this turns out to be related to the two-point function, and I didn't show you this computation. Okay, I transform this to something else, which I don't know. But the good thing is that in random matrix theory, in the regime of omega of order 1 over the density of state, in this regime, so let's just look, I wrote this down, 1 over this is e to the minus s naught, so I have to go to extremely small omega, but because omega is conjugate to t, if I go to the Heisenberg time scale, then I'm exactly probing this regime of omega. So in this regime of omega, we know that this spectral two-point function is universal, independent of what this matrix potential is or what the density of states is. There is a known universal answer. I can sketch for you how it looks, and then I can show you how this double integral transform looks. And that will be the end of the talk. So, this rho correlator as a function of omega, so we fix the energy to be somewhere in the middle of the spectrum. It looks as follows. So eigenvalues repel, and that means that they don't want to sit on top of each other. They don't want to sit at omega equals to 0. So this starts off at 0. And then they are typically spaced at 1 over the density of states. That's the typical level spacing. And because the spectrum is very rigid in random matrix theory, you get a bump, and then you get another bump and another bump at 2 times rho over rho, 2 times 1 over rho v, 3 times, and so on. And at large separations, you converge to the disconnected contribution to this two-point function, rho e squared. Okay, that's the mean density. And if we plug in this expression into this integral transform, we get the following answer. So from the disconnected contribution, we get this eternally linearly growing thing. So that's what we had already in classical gravity. Classical is connected to, I mean, classically we don't get any connected spectral two-point function. We just get this. And from these wiggles, what do we get? At the early time, it turns out that these wiggles only contribute relatively e to the minus 2s naught. So it's extremely small contribution. So this is time. But and I don't have time to justify this too much, but at the Heisenberg time, e to the s naught, their contribution starts to grow, and it grows linearly with a negative slope. So this is coming from the disconnected piece, and this is coming from the wiggles. And a miracle occurs. The slope of this cancels the slope of this, and if we add them up, then we get this curve exactly as advertised. So, I mean, one comment is that these wiggles are actually coming from not just one instanton effect, but the resummation of all instantons, so resummation of the genus expansion. The way to see that is that the scale of the wiggles is 1 over e to the s naught. I don't have it on the board anymore, but the density of states is of order e to the s naught. So the wiggles are happening there, and that you can only get from resumming the instanton effects. But this extremely complicated resummation is completely natural in the language of random matrix theory, where this is a known result since Dyson. Okay, so, and this cancellation is actually something that was not observed before in the random matrix literature, because nobody had the idea of looking at exactly this integral transform of the density point function.
The structure of having this ramp and plateau is supposedly very generic. No, it's you see in all these talks about.
Yes, but the origin of the ramp and plateau of the Stanford group is very different. For them, both the ramp and the plateau are coming from the wiggles. For us, this linear growth is coming from the disconnected contribution. It's coming from classical gravity. It's already there in classical gravity. And and we have a cancellation. The classical effects, or the classical large signal is cancelled by a growing effect of non-perturbative contribution. So indeed, you are right that many people draw these kind of curves, but the origin of these curves is very different. It's just an unfortunate accident. But one thing that physically is very different is that for them, they have a noise on this that is of order the signal. For us, the noise is very small. Is down by e to the s naught over 2. So there's also a quantitative difference if you look at those. Okay. So
it's simple. It's just to understand. So if in the Penrose island, if the black hole is eternal, and it would be defined by theta, which is the inverse temperature, then my poor intuition is if something is eternal, nothing changes because the geometry says food.
That's very good.
What is the thing that is
I understand.
changing?
Yes. So what's changed? That's you can already ask here. Why was the volume changing with time? So it's eternal in the sense of the killing vector field of this space-time, which looks like this here, and is a boost here. But on this side, is like this. So the time goes up on the left, then the time should go down on the right. But here we're going up in time on both sides. So from this perspective, this is not a stationary space. It's a very good question.
Inside, there is no kind of killing vector, right?
There's no time.
Right. Yes.
Yeah. But if we did this time evolution, so I went up here and down here, then the maximum volume slice wouldn't change in time. But this way, I'm actually inducing some non-trivial time evolution.
Mark, perhaps you want to conclude?
Yes. Yeah.
Yes. We can continue discussing.
Yeah. Okay. So the summary is just the following. So we started with this picture of growing interior. Then that led us to considering complexity, but complexity stops evolving in time at the Heisenberg time, and so that led us to ask if there are new non-perturbative effects, and then we found them. Hopefully, we learned something about both black holes and quantum field theory from this. Okay, so with this, I would like to thank you very much for your attention.
So, yeah, what is the volume actually in terms of, say, the entropy or the mass, and does it have a meaning? This maximum volume.
So this is e to the entropy. So the value of the length is e to the entropy. That's where it stops. Yes. And that's the same where the complexity is expected to stop.
And geometrically, does it have any meaning? What it means in terms of distance from the singularity?
Yes, I mean, what it is.
So distance from the singularity. So from this picture, it's clear that it kind of wants to avoid the singularity. Yeah, so it stays in these usual radial coordinates that we like to use. It stays in Z. It likes to stay order one distance behind the horizon. It doesn't want to go down to the singularity. That's true about these real Takanagi surfaces also. Somehow the singularity repels them.
Is it a nice slice?
Yes, it is a nice. It is a nice. But these. So the perturbative gravity effects in this simple model are just boundary gravitons, so they just wiggle a little bit the end point of where you ended. But this effect is coming from topology change, and the fact that somehow in these higher genus surfaces, if you go to large Lorentzian time, it just so happens that the geodesic stops growing, and
But there is no Lorentzian interpretation.
well, there is a tentative Lorentzian interpretation that is not due to us, was discussed by Saad in a nice paper. The picture that he has is that behind the horizon, there are these topology changing processes. And so there's a tendency to grow, but somehow you nucleate baby universes and the growth happens in the baby universe, not in your parent universe where you're measuring the distance. Yes. I don't know if that's the explanation. That's a picture, I mean, that's a picture of how I can make it cross for those of you who are interested. So, so here's this this cutout from hyperbolic space. Here's the geodesic, and you can have a following picture that you have some topology here. And the point is that in large Lorentzian times, this handle grows very big. So if you drew a geodesic through it, that would be very long. But there's a shortcut, and so it stays constant. I mean, stays constant at this large value. That's a picture.
So there are in fact two ways in logography to describe the complexity. One is the volume, and the other is the action. And you treated just the volume.
Yes.
Would you get similar results?
That's a good question. I don't know what the action means in a fluctuating. I mean, I was doing Euclidean, and this action is the action of some Wheeler-DeWitt patch of the Lorentzian spacetime. Maybe it's possible. I mean, it could be possible that you can find some nice Euclidean counterpart of this volume of the Wheeler-DeWitt patch, but I don't know what that would be.
And some this behavior that starts at the to the S with something we would expect in any dimension.
Yes.
But right now we do it only on shade T.
Yes.
That would tell us that in general we should rethink ADS-CFT as ADS dual to a random system, or on one CFT I get the same drawing.
Yeah, very good, very good. That's actually something I wanted to say. So this expression that I have there is very easy to convert to something that looks reasonable in one system, and that would be a double sum over the energy spectrum, E1, but missing the E1 equals to E2, 1 over E1 minus E2 squared. This E means the sum of the center of mass of the two E's. And then I have 1 minus cosine E1 minus E2 P. Okay, so if you define this quantity for one quantum system, then if you take an ensemble of these quantum systems, then you exactly get this. The 2-point function comes from converting these sums to integrals. Okay, so this proposal for one quantum system is such that for an ensemble of quantum systems, you get agreement with that. So you could try to compute this for any chaotic quantum systems you like. And I'm telling you that you would get this curve with very small noise on top of it. And so we've actually done this for SYK. Of course, it would be nicer to do it for super young bits, but we don't know the spectrum of super young bits. But if we would, then you could compute this. And our proposal is that this would have to do with the maximal volume in type 2B string. Whatever that means in that. Or in supergravity, it would definitely have something to do with it. But I mean, we did an S-wave reduction, so I'm not saying we are capturing all the effects. There would be other effects. Maybe that would modify this simple-minded definition. But it has to reduce to this in simple models or in S-wave reduction.
Yes. In 3 dimensions, in ADS3, there was this old figure by Mezei on the unitarity problem where he had 2 local operators at different times, and then he showed that they cannot decay exponentially forever at some time e to the S0, right? There should be other effects.
Yeah.
But there, the effect when you do the functional integral was due to configurations that were not black holes at all, right? So for instance, thermal ADS. So here we are probing the same time scaling, different model. So But why is the thing that you're computing related to a black hole? Couldn't it be that you are looking at times that are so far away that actually you cannot tell between black holes?
Yeah.
Thermal ADS.
I agree with you. It's not clear that these higher topologies, like this one, has whether it has an interpretation of a black hole or something different. Or my only point is that we tried a reasonable definition that is gauge invariant even when including higher topology, and it gave this result. Maybe somebody else can come up with another completion or gauge invariant definition that reduces to the same in the classical limit. I cannot rule that out, and maybe that would show different behavior. All I'm saying is that this definition of drawing geodesics even on higher genus surfaces led to this result. So yeah, all the subtleties hiding in the non-perturbative definition in quantum gravity. So it's unclear if this is thermal ADS or if this is black hole or nothing.
Okay.
Thank you
No
so
more
much.
questions? Thank you again.
Mark. So do you expect there should be some geometry